Now let's talk about the analyzation phase with process capability. It's helpful to think of process variation and capability as limits. They can be customer figured or formulated. They tell us the specification of the limit and the control limit. Remember, we want to work toward less process variation for a higher process capability. That's the picture on the left. This means that our process has little variation, which in turn means far fewer defects. Anything that falls outside of the spec limits is defined as a process defect. These are distribution curves. Normal distribution is a data plot that appears as a bell-shaped curve like the picture to the top right. It is symmetrical with the process mean near the peak of the curve, and it's defined by the mean and its standard deviation. Every process has natural variation in their output, and the greatest number of results end near the middle of the measurement. Non-normal distribution is a bell curve that is skewed based on the tails. As you can see, there can be a negative skew or a positive skew. Also, the mean is not aligned with the peak of the curve. It does not use standard deviation since the curve is not symmetrical. When performing analyzations and calculations for a data-driven project, it's important that you have the right tools to get the right analyses and the right graphs. The software program that we use here in the ALUSA Continuous Improvement team to run these analyses, measure process capabilities, and create control charts is Minitab, which is a Six Sigma software. To learn more about how to use Minitab, reach out to any one of the CI contacts listed at the end of this training. Now I'd like to walk you through how you would calculate normality. In all cases, when we analyze our projects, we use the Minitab program. In the program, we can run a test to check if our data is normal. Minitab creates graphs and generates the statistics. It calculates the p-value, which is a type of inferential statistic that measures confidence. We always assume that the data is normal, and a good rule to remember is that if the p-value is low, the assumption has to go. The industry standard is to use a 0.05 threshold for the p-values, which relates to 95% confidence. In this case, the p-value is above 0.05, so we know the dataset is normal. Just a couple of practical notes. For non-normal data, as mentioned earlier, the curve is going to be skewed, so use the median instead of the average. Also, Minitab is a best-in-class Six Sigma tool that can be used for a number of other analyses, like checking for randomness.
So let's take a look at how process capability is actually calculated. On the left, you see a graph that represents the actual performance that we've observed. So the blue bars are the actual measurements that have been collected. The line or the bell curve is calculated from those blue measurements to really represent the process performance or the process capability. Below on the bottom right shows the calculations that correspond to both the blue bars and the curve. So a lot of times in Six Sigma we talk about defects per million opportunity. That's circled on the left. So in this case 653,000. Based on that curve in the graph, there would be 653,000 defects if this process was run 1,000,000 times. Earlier we talked about sigma levels. So again, on the bottom right of the visual, it shows 1.11. That actually corresponds to the 6 sigma level. So currently, this process is performing at a 1 sigma. The higher the DPMO, the worse the process capability. And as project leaders, there are things you can do to either shift the curve to the left so that more area is within the upper spec limit, or reduce the variation. Let's take our discussion of process capability further. Let's actually look at a case example. So if a company manufactures a product that has an acceptable dimension between 155 and 157 millimeters, how does that relate to process capability? The graph below shows, again in the bars, actual samples that have been collected, whereas the lines represent the process curve. On the right, we talk about additional capability metrics. So before we've talked a lot about DPMO, or defects per million opportunity. There are also additional ways to think about process performance. So on the PP or CP view, these monitor spread, or as they compare to the specification. Whereas on the CPK or PPK, the process is really centered around your target. Kind of more to come as we talk more about CP and CPK. So let's first start with variation. PP is a term that's really based on the estimate. So this looks at the sample and estimates out the standard deviation for the group. Whereas CP still relates to variation, but this is calculated based on the true values. So in a lot of cases, you may have enough data points or maybe a stable process where you don't need to calculate based off the estimate, but you can use the actual numbers. At the end of the day, we're trying to understand and trying to ask the question of, are our processes capable? So we want scenarios where our CP numbers are greater than 1. These numbers are automatically generated out of the Minitab software, but it's important you know what to look for. So on the visuals on the right, give a more detailed scenario. So let's say if the truck was our process capability. The customer specification is the garage. So in the different scenarios, if the truck was larger than the garage or our process is outside of the specifications, the CP number would be below 1. If the truck matched the garage exactly, the CP number would equal 1. In any case where our process was well inside of the specifications, that's great. Our CP numbers will get generated as above 1. Again, these are additional metrics to measure and quantify process capability. Now let's think about, is our process acceptable? A capable process does not necessarily mean it's acceptable. So even if from a variation perspective, the process or the truck was small enough to fit in the garage, it may be missing the mark. So if we go back to the example with the garage, the truck represents our process capability, the garage is our customer spec limit, and maybe there's some disruption that's forcing the truck either left or right. In the case where our CPK numbers are below CP, the truck has missed the mark. So it may be able to fit within the garage, but maybe it's shifted to the left. We want to look for cases where our CPK number is spot on or equals our CP number. This means not only is the truck able to fit in the garage, but it's also centered to the point where it can fit in the garage. If the CPK numbers are considerably below the CP numbers or drastically below, the truck is so far off center that it may be outside of the customer specification limits. So it's important, if you think about process capability, to know if you are, from a variation perspective, within the specifications, and also from a centering point of view, to know if you are off center, which may be causing you to be outside the specifications as well.
There are a few ways to express the process capability, via CP, CPK index, or with sigma level. Either way you state it, the outcome is that the DPMO will represent the probability of defects out of 1 million opportunities. Understanding and improving CP, CPK, or the sigma level reduces the opportunity for defects. So let's take a look at a few data examples. We'll look at both a continuous and then a discrete example. For the continuous example, we are measuring the cycle time of our main process. Keep in mind, the topics here work for any continuous data set. Here we collect 10 samples. Historically, before using Six Sigma, we would probably know the average, understand the worst cases that our customers complain about, and know overall that we need to get faster. This is a limited view because we may not understand the overall process capability nor have clear goals on what we are trying to accomplish. Once we view this information with a Six Sigma lens, the data begins to paint a different picture. We can use basic statistics to measure both the average and standard deviation of this continuous data set. Also, note that we'll need to establish a goal so we can measure the process's capability towards that goal requirement. In this example, 6 samples did not meet the set goal of 7 days. We use Minitab to generate a graphical representation of this process. Finally, Minitab calculates the process capability. Based on the statistics, this process is performing at a 1 sigma level, or 685K DPMO. We can use the same tools for a discrete project as well. Imagine if we were measuring customer complaints. Now, we focus a lot on the number of non-conformances, and there may be times when we lose view of the total volume going through the process. It is important to note that both the total volume and the number of non-conformances are needed to understand process capability. For discrete data, know that a bell curve will not be generated. If we decide to trend this data, such as measuring complaints per week, for example, we would turn this into a continuous data set. However, Minitab is still able to measure the process capability for discrete data sets. In this case, the DPMO calculation is straightforward, and looking at the calculation results it gave us, we know this process is performing at 400K DPMO. Next, you must define your performance objectives. There are 3 types of performance objectives that you may set. The first, benchmarking, is the highest world-class performance. Z short-term is simply the level of performance a business should be able to achieve given the investments already made. And the baseline monitors the current process. Now you must identify the variation sources. These identify factors that are preventing the process from performing to the customer's expectations. Consider what factors are causing your defects. Is the issue variation? This means the standard deviation or range is causing far too much variation. If the issue is centering, then that means the average is far from the target. Or perhaps both are causing defects. This chart you see here helps us identify the tools we use to prove factors are vital.
So let's look at one hypothesis test. In this case, we're looking at the 2-sample t-test. If there are 2 different populations that have different averages or different means, is the red team on average quicker than the blue team? This test will help you analyze their performance as well as statistically prove if there's a difference. It's key to note that for any hypothesis test, you want to start off with the initial assumption, or the H0, thinking that both populations are equal. It's only then that you want to run this test and prove if that's true or not. So one practical note, both the t-test and other tests like the homogeneity of variance, or HOV, can help project leaders prioritize their improvements. Is it important to focus on the groups that have a lower mean or average, or is it more important to focus on groups that maybe have a different variation? These tests can help any project leader make that decision. There's a lot more to be learned within Greenbelt training in person, but here we wanted to introduce the concept in our online session. So let's assume we ran a test for 16 data points, and we were interested to see if there is a difference in the averages between the 2 samples, or 2 suppliers in this case. So we can see here, supplier 1, we looked at 7 samples, has an average of 17.29. Supplier 2, we looked at 9 samples, and they have an average of 18.56. So even though those numbers are actual different numbers, statistically the question is, are they making a difference? So, is it a big deal that supplier 1 is giving us 17, whereas supplier 2 is giving us almost 19? We really want to look at the p-values. So in Six Sigma, as we mentioned earlier, there's a big focus on inferential statistics. How confident are we that there's a difference between these 2 data sets? And in Six Sigma, we look at the p-value as compared to 0.05, or the inverse of that will give us 95% confidence there's a difference. So in this case, the p-value is 0.49, and which is above 0.05. So we necessarily can't conclude that the suppliers have different averages. Even though 17 is less than 18, statistically it's not significant enough to say that there's a difference and we need to treat either one of these suppliers with follow-up actions.
Now, let's talk some about correlation and regression. Correlation establishes if a relationship exists between variables and answers the question, how strong is the relationship? Regression describes the relationship between variables in more detail. It can be used to build predictive models using simple linear regression, that's one predictor, multiple linear regression with multiple predictors, or polynomials with non-linear regression. Let's take a look at these scatter plots of our data. Anything that charts upward is a positive correlation. Anything that charts downward is a negative correlation. Tighter spreads indicates if it's strong or not strong. Scattered data points that go neither up nor down indicate no particular correlation.
So there are a number of hypothesis tests that we can run in Six Sigma. At the end of the day, we're trying to reduce down all the factors that may have an impact on our output or our project Y. We're trying to identify which ones are statistically significant. So think of it as a funnel, like on the right. In any project, there could be 30 things you can go fix. But the question is, what are the top 3 or 4 that are really having an impact on your project Y? What are those things that are significant enough to go investigate? We want to be able to screen those potential causes. We want to be able to narrow down those vital few X's that have a very heavy relation to the project Y.
Here on the impact prioritization matrix, we want to define tasks according to their effort and their impact, and to understand where the quick wins lie. Simply list your project deliverables and then chart them based off of how much of an impact it will have versus the amount of effort you will spend to accomplish this. Deliverables with the highest impact go near the top. Deliverables that take the most effort to complete go to the far right. It makes sense to first tackle the deliverables that have the most impact for the least amount of effort.
So moving on from improve, let's go to the last phase of Six Sigma, which is control. The first step of control is actually doing a measurement system analysis. So this should look very familiar from the measurement phase. In this step, you really want to confirm that your measurement system hasn't changed after the improvements have been in place. You can do measurement systems on the initial data that you did, so your project Y, as well as what were your X's. So for instance, let's say if we were implementing solutions in a transactional process and we wanted to put in a rejection rate or a rejection process or a kickback process. How could we do a measurement system on the actual improvement of the rejection process? Can other people detect when things should be rejected or pushed back? This is really doing an MSA on your X that may impact your Y. Step 14 in control is all about doing your process capability again. So this is a great place to show the before and after improvement. In Analyze, you ran process capability to get a picture of how the process is performing before any improvements were put in place. After the improvements are implemented, you want to run your process capability again, and in this case, you want to show that the DPMO has improved. The last step of Six Sigma is ensuring things are in control. So you can do this both qualitatively or quantitatively. From a qualitative perspective, we talk a lot about poka-yoke, which is a Japanese term for mistake proofing. In this case, you want to think about what are the things that I can implement to ensure that the process does not change. So the last step of control is looking at control charts. So there are 4 types of control charts, and the one that you use is really dependent upon if your sample size is variable or constant. Also, it's dependent upon if you're looking at defects or defectives. This is something we covered back in the Analyze phase. So by the time you get to control, you should know whether your project was associated with which type, especially for discrete data. So let's look at an example. For a C chart, it's really looking at a sample size that's constant as well as defects. So if we were looking at OSHA recordables for a plant, the subgroup size would be constant, the plant, or the number of people at the plant. Probably would not change too much. So even though there's a high opportunity for defects, injuries that occur are actually small. And so the defects of a injury can be plotted. Those are not necessarily defective since one injury equates to one defect. So in this case, we use a C chart, as you see below, as an example. Over the course of some time, you can plot how many injuries actually happened. The upper control limit is statistically calculated, like we shared earlier, and that doesn't necessarily change since the sample size doesn't change. Any points outside of that control limit would be considered out of control. And for any process leader or project leader, you would have to go investigate as to why that's out of control and implement some process improvements to get it back in control. By the time you've implemented your improvements in the earlier phase, you should be seeing your projects within control. And if that's not the case, it's important that you go back and investigate or look at additional improvements that can be implemented.
Finally, we need to establish a control plan. The control plan helps us describe the actions that are required at each phase of the process to ensure that all process outputs will be in a state of control. This is a living document that reflects the current methods of control and the measurement systems that are being used.
So now you've completed the online Yellow Belt course. Thank you for taking the time to complete this session. Please navigate back to the curriculum and finish the second test. If you're interested in hearing more about Yellow Belt content or learning more about continuous improvement in general, feel free to reach out to these contacts. You can reach out to Rakesh, myself, Natasha, or James. Thank you.